So these first ones are just regularized tables. There's no tricks that we can use to make them simpler. They just are what they are. But we are going to see some places later where we can use some tricks to simplify the math so we don't have to do as many quadratic formulas. Which on any test I will give you the quadratic formula because right now I can't remember the whole thing exactly. Is it negative b minus 4 or minus the square root of 4ac?
It's minus b plus or minus square root b squared minus 4ac divided by 2a.
B squared minus 4ac, that's what I was missing. Divided by 4a. So I will give you that. You need to know how to use it, but also if you have this calculator or a calculator that does a polysolver, you're welcome to use that. If you don't plan on getting one before the next test, though, you should practice working through the quadratic formula. I guess we can do a few of those. Okay. So our ICE table is initial change end. What is the initial? Close. The problem is we need concentration. Yeah, so when we're doing any of these equilibrium ice tables, everything has to be in concentration. If you're doing just stoichiometry ice tables, you could use just moles. But because the equation for, or law of mass action, those are concentrations or pressures of products over reactants, everything in the ice tables that we do for equilibrium needs to be in molarity. So we're going to take these and divide them by, take our moles, divide them by volume, so 0.5 divided by 5.25. 9.5. Let's do 9.52. Yeah, we should go to 8. And then 0 of the product. And usually I try to line this up a little bit better, but those numbers are kind of long. Then I'll put a line here. Especially on these, you don't need to write out all of the decimals. All of the decimals is too many. So like on this one, I went like 2 past what the last sig fig would be. Ideally, if you can keep it in your calculator, then you could just keep those numbers in the calculator. Which way is this reaction going to shift? To the right. Towards the product, right? Because it's 0. Which means that my changes are going to be negative x, and plus 2x. And at the end, this will be 0.095238 minus x, 0.095238 minus x, plus 2x. Just keep in mind, the whole reason we can do this is because we're trying to find equilibrium concentrations, and we know K. So we know that whatever this ends up at is going to equal K. Where do I want to put this? I'm gonna put it up here. So this ends up being 2x squared. And again, anytime we're doing ice tables, you want to try and simplify things as much as possible. So because my starting concentrations are the same, right? These concentrations would go on the bottom, or my reactant concentrations. But because both of these are the same, I can just write this once and square it. Another tip that leads to a lot of really small mistakes is this 2x, when you write it up here, it's the whole 2x in parentheses squared. So it becomes 4x squared. But write it in the parentheses so you don't forget to square the 2 also. So then this down here is going to be 0.0952238 minus x squared. $54.3. So what can we do to make this simpler? Yeah. If the top here is squared and the bottom is squared, I can take the square root of this whole side and the square root of this side, and I can just drop the squares, which is really nice because then I don't have to do a quadratic formula. And so that's why I wrote this out as parentheses 2x parentheses squared instead of writing out it was 4x squared, because it's a lot easier to see that I can just take the square root of the top and bottom. So if I ever give you a problem on a test where like the reactant concentrations are the same like this, or like the product concentrations are the same, I'm trying to be nice and give you a way to make it simpler. That being said, you could just square those, you could do the math, you could do the quadratic formula, you'll get the same answer. It'll just take longer. So then we get 2x over 0.095238 minus x. And then whatever the square root of 54 is. $7.368.5. Again, trying to save a little bit of time by not writing out all of the decimals, but keeping them in the calculator. So now we just solve for x. So I'm going to take both sides. I'm going to multiply by that denominator. Actually, I have that number in my calculator too. So we're going to get 2x equals and then add that x. So this becomes 9 point. So x equals 0.074907305. Ow. Actually, I don't want to set. questions. I'm not quite done yet. So the last thing we need to do, because we're looking for concentration of all species at equilibrium. We found X, we found the amount that everything is going to change by, so we got to plug that back in. So 0.095238. This times 2. So all of my species, H2 and I2 are, and then HI. Oop.
Looks like you're saying H2 plus I2 is equal to that.
Oh yeah. Nobody likes my and. Wait, can I do an? Ooh. Fancy. Ampersand. It's kind of a capital cursive S.
Looks like you're using that. I don't know which
Cleft.
one.
Treble cleft.
Sure. Can't you keep it in moles and at the very end, kind of in volume, still in the same number?
I don't know. I would want to try it first. You're saying that you can
Yeah.
keep it in moles?
Keep it in moles, but just make sure
That makes sense.
you don't get elite decimals like that until the very end.
Good. Questions? You could also check our answer. Because now that I know these concentrations are at equilibrium, they should equal K when I plug them into the equilibrium equation. So 0.15 squared divided by 0.0203 squared. Probably rounding error. So it should be 54.3. Squared because they're both the same concentration. Comes into 54.6. But I did round these. I used these rounded numbers. I think if you use these, you'd get closer to 54.3. Not as bad as the rounding error in, yeah, experiment 6. That was wild. I was wondering why so many people were off, and then I saw that people were like rounding it for the answer that they were putting like in the box.
Yeah.
And I saw that it was getting used, but I didn't think it would make that big of a difference.
If you use same figures, you got a completely different word. No,
Yeah. Sig figs are for final answers.
That's what I always thought, but I always kept on getting docked on sig figs in like my lab reports last semester for Chem 1. I was just like, I don't want to know anymore.
Well, like the number you write in the box should have the correct sig figs. The
Yeah.
number you use in the calculations.
That's how I always did it, but I always got docked
You
somewhere,
got-
so I just
oh.
kept up.
Well.
Maybe you're just making sig figs.
Okay. Another?
I don't have to trust well, it's a different context now.
All right, so we've got new reaction. And we have the concentration of 1, finding equilibrium concentrations. Essentially the same problem, except now we have the product's initial concentration. But still initial change and so it's going to be negative x, or sorry, this is minus 2x plus x, that's x, and this is 0.100 minus 2x. All right, now I can plug them into the equilibrium expression. I can't really do any nice simplifications on this one. Right, taking the square root of both sides wouldn't really help me because I get this 1/2 x. Yeah. I don't know. You could probably make it work. I don't think it actually makes it nicer to work with, though. So we are going to have to do a quadratic formula eventually. You also have to remember whatever it's called when you do this, you expand the polynomial. Is that what it is? Or is this the opposite of expansion? Actually, I'm just going to write that part, right? Either first, outer, inner, last. Oop. That's going to be 0.01 minus 0.4x plus 4x squared. You'll get really good at that. And move the x there. Question? This whole thing? Yeah. Do I have? It has been so long. What class do you, is that an algebra thing? So it's called or at least what I learned was the FOIL method. Or actually I should write it sideways. So it's first, outer, inner, last. You got it? Oh, okay, okay. Sorry, what? Oh. Okay. Anybody else want me to go over the? Well, it's fine if you want me to. You do one. No? Okay. It's got to shake loose some cobwebs. Yeah, so I just expanded this one here to do this to make it a little bit, to try and make it more visual so you can see it more. All right. And then I need to move the x over. So this is 0.01 minus 0.76x plus 4x squared equals 0. And now, quadratic formula. Negative 0.7601. So we get two different x's. And x2. So which of those makes sense? Yeah, only the first one makes sense. And it makes sense because if we look up here, mostly you're looking at where you subtract. Because if I try to do x2 here, 0.175, I can't even subtract one of those, let alone multiply by 2 and then subtract it from 0.1. That would give me a negative amount of this. So that one doesn't even work. And that should always be the case. You'll get one that works and one that doesn't. One that's real, one that's imaginary. Although, not technically mathematically imaginary. That was loud. Okay, so this is 0.014225. And actually, I could just say, whoops, N2O4. And then for the other one, this is 0.071554. We should, of course, check. Yep. 0.0716 squared over check. Actually, does it work rounded? Close. Again, rounding error makes it a little bit off, but it's close.
Also, I have a question.
Mhm.
So when we're showing our work for the rest of this, do you want us to show the work when we're plugging in X, or can we just leave it as is to save space?
Like this part, or I do kind of like on, I think I mentioned this yesterday in lecture, I do want to see a few more decimals past rounded. This is not as bad as on the lab, because on the lab, especially when it says just round to the nearest integer, it's kind of like, well, how close was it to that integer? I think somebody did they got like 0.46 and they rounded that to 0.5 and then they rounded that to 1. And I thought that was, well, doesn't work that way, but it was also,
You can't be wrong there.
it was also kind of clever.
Keep rounding till you get the number you want.
So if we just write it as this, we'll get a full mark.
Yeah,
Okay.
yeah. Yeah, showing, yeah, as long as you get most of the other work, and X. Any other questions? Yeah.
Do we just ignore like the temperature that it's at? Like is that just extra information?
We are not doing anything with it yet until, I can't remember which chapter it is, but thermodynamics. The temperatures, it's important because the K is only for a single temperature. So if the temperature changed, then a temperature would be, or K would change, and then we couldn't do any of this. So it is extra information on this worksheet, yeah.
Damn. I forgot the science calculator has one.
Whenever you do gilmans, it has to be like 25C or something, right? Like for this to work. It's like a certain temperature, it has to work that.
No.
Sure. This could work for
I think you have like standard states, I think. Because like not, a lot of these aren't at 25C. All right. Let's see. Where do we start getting? Because I think it's the last one. Well, I'll do one of these, and then we can go on to the approximations. Yeah, so far these don't change very much, but now instead of one of our products or reactants being 0, we need to actually figure out which direction this reaction wants to move. So we got 0.100 and then 0.100. That's a weird 0. And 0.100. So that's my initial. I'll have some change. I'll have an end. So we need to calculate Q. What's the difference between K and Q? Or what makes Q different from K?
Doesn't need to be in equilibrium.
Yeah. Q doesn't need to be at equilibrium. K is always at equilibrium. Q is where we calculate just for, in in this case, whatever concentrations we have. So we're told we've got a reaction mixture, initial concentrations, and then it says find equilibrium. So it doesn't say specifically that we're not at equilibrium, but it does imply that we're not in equilibrium, and that's where we're headed. But which way is that? So this is going to be 0.100 squared. Really over, I'll write it out this time. So Q is, no, Q is 1. Yeah, Q's just 1. Because it's 0.100 squared divided by 0.100 squared. So Q is 1, my K is 81.9. Which way is this reaction going to shift? Towards the products. And I'll keep saying it, whether or not it sticks, but this is a ratio of the concentrations of products divided by concentrations of reactants. Q of 1 means that essentially the concentrations are the same. This means I need more products. So if Q is smaller than K, I need to make the top number larger, I need more products, and so we're shifting towards products, which is important because when I write down my change, I need to know if I'm writing plus X or minus X on either side. So we're shifting towards products, so this will be plus 2X, this will be minus X, minus X. And then in the end, and I think it's a good idea to write out these extra zeros, quote unquote extra, right? They won't change the calculation. And I won't say anything about it as long as your sig figs are right at the end. But if you get to the end and you give me 1 sig fig, I'm gonna say maybe you should write those zeros. At least on this table. After that, probably not such a big deal. This is 0.1. Here, I'll do it. 2x, 0.1 minus x. And that's got to equal 81.9. And we can simplify again. Because I got something squared over something else squared. So if I just take square roots of both sides. Then this is 0.1 plus 2x, 0.1 minus x equals 9.04. And oh, yeah. Uh-oh. Oh. Perfect. So I checked my answer on the calculator, found out that I had forgotten to do something. This is a nice thing about ice table problems, actually. Equilibrium ice tables is you can check your answer because it should give you K, or at least really close to K, depending on how much you rounded. And if it doesn't, then you get the fun job of going back through your math and figuring out what you forgot. So yeah, really for these two, you can't, if you don't have a zero, right? If you have a zero as one of your concentrations, it's always going to move towards the zero. If you don't have a zero, you can't really make any assumptions about which way the reaction is going to move. And so you need to calculate Q, figure out which way the reaction is going to shift, and then you could do all of the regular ice table stuff. Yeah.
Can you explain how Q has to be
Yeah. So Q, you could just memorize, like if Q is smaller than K, then it's going to go towards products. Yeah. Do it that way. If Q is larger than K, then we go towards reactants. really it has to do with the ratio. So like here, like if you look at the numbers we started with, everything was 0.1. So pretty even-ish. And actually Q came out to be 1, so the concentrations are the same. But in my final answer, my product concentration is a lot bigger, 10 times bigger than my reactant concentrations. And so our K is much bigger. So like that's why in lecture I was saying if if Q is less than K, and it's products over reactants, then Q is less than K, then the products are too small, and the reactants are too big. And so you move from the one that has too much to the one that has not enough. And that makes that fraction top heavy, which makes it larger than 1. So we do like the first part of this next one. Oh, it was in the other room. So yeah, actually keeping that in mind, without calculating Q yet, if our K is 50, that means I should have, at equilibrium, more products than reactants. So based on these concentrations, initial concentrations, just sort of eyeballing it, do we have more products than reactants? 0.08, 0.06, 0.79. So we already have more products than reactants. And so this probably isn't going to shift farther to the right. It could still. We could still be short of K. We could need more. And I'm cheating a little bit because I did these earlier. But my guess would be that if we are already shifted over to the right, it's going to come back to the left. But that's why we calculate Q, because it's not easy to just look at the numbers and sort of guess which way it's going to go. Square. Yes. I've just been writing these in with all the numbers, but does anybody want me to go over how I got this? Is this good on? So Q, yep, Q is 130. So we're actually maybe not very product heavy, but we're product heavy. There's more products than there are reactants at equilibrium because Q is larger than K. I'm going to leave that one leave that one for you guys to do. Because I want to talk about simplifying. It's always the best when you can make the calculations shorter and easier, especially with ice tables. So our first simplifying approximation is called the 5% rule. And you can use this when K is really small and you're starting with reactants, or if K is really big and you're starting with products. And the reason is, if K is really, really small, what does that say about my products versus reactants? What? It's going to be mostly reactants in equilibrium. It's like I won't have very much product. Because this is a very, very small number, a lot less than 1. It'll be mostly over on this side. So if we calculate the concentration, 5 divided by 10. And then here we're starting with 0 of the product. So we don't have to calculate Q. We know which way this is going to go. But the key here is that it's not going to move very far. Initial change, equilibrium. So my initial is going to change by minus x. This will be plus x. This will be plus x. Everything the same so far. And then we can write this as x squared over 0.5 minus x equals 8.3 times 10 to the negative 4. So x is not going to be 0. But one of the questions in the rate law lab? Yeah, the rate law lab. We're going to ask you to calculate the 2 different factors. One of them has the hydrogen concentration in it. Ends up being really, really small, so small that it doesn't matter. Or as I explained in my Chem 20 classes, it's like holding a baseball. It's talking about the size of an electron versus a proton. If a proton's the size of a baseball, then an electron is the mass of a grain of rice. And I always say, if you put that grain of rice on top of the baseball, or somebody put that on top of the baseball and your eyes were closed, you wouldn't even notice. And that's what we're saying here about my starting concentration of, in this case, phosgene, outlaw chemical weapon. The amount of phosgene that actually reacts to become these things over here is going to be really, really small because my K is very, very small. It's favoring this side. So when I subtract, whatever I'm subtracting from 0.5, it's going to be close enough to 0 that I can ignore it for this factor. Over here, where my concentrations are going to be x, I'm adding it to 0, so I have nothing. So there's nothing too small that would be considered insignificant. So in this equation, instead of having x down here and then ending up with a quadratic equation, whenever k is really small, we can assume that x is so small that it doesn't matter. So it basically goes to 0. And then we can solve this as the simpler x squared over 0.5 equals 8.3 times 10 to the negative 4. And then we take square roots. Yeah, that's a really small number, but is it small enough? And that's why this is called the 5% rule. When we make this approximation, we want whatever x we calculate to be less than 5% of the number I'm subtracting it from. So to check this, we take 0.020337 divided by 0.5 and then times 100 to make it a percentage. And that comes out to 4.07%, which is smaller than 5%. So this becomes these are please always circle your final answer. Circle, box, highlighter. So much easier to find.
Dude, can you see it?
Hmm?
And see on, wait, no, I think it's wrong. Wait, no. I think there is a missing 0.
Did I miss a 0?
And C only C only too. Because it was 203,715.
Oh. Yeah. Well, now I want to see also how off is my... Like if I try to check this, how off... I missed a 0. It's supposed to be 203. And I haven't checked my answer yet, so... How far off will I be? Pretty far off. Good catch. So this is 479. Yeah. So what about when the small, it's like we don't get this approximation is less than 5%. If you do an approximation and it's not less than 5%, then you can actually take that number, we'll see this in the next one, take that number and replug it in for this x that we assumed was 0. And then you calculate x again. And then what happens is, as you keep re-entering that x in, you shouldn't have to do it more than a couple times. Because you shouldn't be using this approximation unless you have a really small or really large k. What happens when you plug that approximation back in is you're sort of making an intelligent guess and check, and it will narrow down towards some value. And so when you keep getting the same value out of that calculation, you know you've reached the right value. So this next one, same reaction, so I'm going to rewrite it. We again have COCl2. Oh, it's 0.1 mole divided by 10. So again, this is minus x plus x plus x, and our k is and the big difference between this problem and the last problem is I'm just starting with a smaller amount. But because I'm starting with a smaller amount, the amount that shifts over will be a larger portion. And so when we write this as x squared over I would say it's still worth trying the small x approximation. Because our k is still small. It's closer, x squared over and we need the square root.
Just always assume small x.
I need to try it with the other problems. Like if it's not even close to being small. How many times do you have to approximate in a loop before you actually get to a single answer? have a feeling it will take too many times. It'll just be easier to do a quadratic. So what do I need to do next? Check if it's actually 5% or smaller. So I take that x, and I'm going to use green. So 2.88097 times 10 to the negative 3 divided by 0.01. And that is, sometimes I need like a happy medium between scientific mode. That's times 100, that's 28.8%. So it's not less than 5%. And at this point, you can make a choice. You could either go back and solve it as a quadratic, because you don't have to use a small x approximation. Or we can take this number and we can plug it in for our x that we had before. So this will be x squared over 0.01 minus 2.88097 times 10 to the negative 3 equals and we solve for x again. Actually, I should highlight these because I took this x, and then because it wasn't smaller, I plugged it in for this x. Because it wasn't less than 5%. So 0.01 minus 2.88097 e to the negative 3 times 8.3 e to the negative 4 what is that? 1, 2, 3, 4, 5, 6 5.909 times 10 to the negative 6. And then the square root of that. .4308 times 10 to the negative 3. Now that's not that much smaller than the number that we got. So this is still not going to be less than 5%, but that's not what we're looking for anymore. After the first less than 5% doesn't pass, we're just looking for this number to not change very much. So between 2.43, 2.88, it didn't change very much, which means we are close to a good approximation of x. We could do this again, which is where if you're really quick with your calculator, we can do this again pretty quickly. So doing this another time gives me 2.506 times 10 to the negative 3. And then if I do it another time, what do I use? Green, red, purple. So So our first approximation, we got this 2.88. We said that's not less than 5%. If I do it again, I get 2.43, which it changes some. And then I get 2.5, which really isn't changing much at all. And then doing it another times 2.49. So we sort of converged on whatever x it is. And by plugging x in, I'm just plugging in what x actually is. So, I don't know, you could practice doing this on your calculator. But let's use, because really if you do it twice, let's use this number and then we can check, because I can plug in this x and I can see if my final answer actually gives me k. All right, we can always plug it back into the law of mass action. So what was that? That was the green. Point 0.01 4308. And then these ones are just going to be 2.4308. So this is 0.0075. And then 8. It's pretty good. So if I plug these back in to calculate k, this equals which is pretty close, but not perfect.
Is your x not right?
It's pretty close. I mean, 7.8. If I do the red, that comes out to 8.3 times 10 to the negative 4. Normally, I would say if you get to, it's not less than 5%, just do the quadratic formula. But I think if you do this and you don't get less than 5%, if you do it a second time and it changes more than 5%, so like the change from here to here is less than, it's like 3.1% change. But the change from 2.88 to 2.43 is a lot bigger than that. Yeah, it's like 16%. So from here to here is a 16% change. From here to here is 3.1%. So again, you're looking for a change in X of 3.1% or 5% or less. And that got us to a good approximation. So it's kind of up to you how much that makes sense and how much that seems like a shortcut and how much that seems like a lot of messing around. And maybe finding out.
So this is just an alternative to quadratic.
Yeah.
But quadratic formula will still give the correct answer.
Yeah, when we're doing this for finding an approximate solution, when you do the quadratic formula, you're finding an exact. And for a lot of things, the approximate's good enough. Okay, we have, actually, should open up. Any questions about that? Yeah.
It's not really a question, but you want us to redo it, find the answers using the red?
Yeah, because the red did give almost exactly the same answer, or almost exactly the same K. Yeah, 8.38 times 10 to the negative 4 versus 7.8. And actually here, I'll show you. Did I solve it exactly? Oh yeah. So earlier when I did this, I solved it with the quadratic formula and got 0.00249, which compared to what we were just looking at in the red is 2.506. And then even when I did the approximation again, I got 2.49. So I did reach the same answer. And you would always get the same answer. You don't have to do any approximations. Any other questions? All right. So there's another one for you guys to do. I think this is the last type of example, yeah. Yeah. So the difference on this one so the small x approximation works the best when you have really, really small k values or really, really large k values. So our last problem was like 10 to the negative 4. Now we're at 10 to the negative 8. That's not half as much. That's 10,000 times smaller. So this is a very, very, very small k. The problem is, in this, as it's written right now, I can't use the small x approximation because I have reactants and I have products. The neat thing about equilibrium, though, is it doesn't matter where you start, we'll end up at the same equilibrium. That's probably a good rule of thumb. I think it's even better because, like on the last one we saw, We use 10 to the negative 4. So Jonathan was saying like rule of thumb is like 10 to the negative 3 to 10 to the negative, or actually really just greater than 10 to the negative 3. Or smaller than 10 to the negative 3. You could use small x approximation. But it really matters, what really matters is the difference between your value of k and your amount that you're changing. So like this would be 10 to the negative 2, this is 10 to the negative 4. So the difference is smaller than 10 to the negative 3. If this was 8.3 times 10 to the negative 5, then our smallest approximation would probably work on the first try. So whatever concentration you have, if it's at least 10 to the minus 3 smaller, or 3 decimal places over, I guess. Okay, so how do we make this work? So that we can use a small x approximation and use it very reliably. We want to push everything over to one side. We want to push everything over to the side that's not going to change very much. So very small x means that my reactant concentrations are going to be really high, my product concentrations are going to be low. So if I push all of this over to the reactants, then my reactants won't change very much, and my products will change by just a little. So we have to do some stoichiometry. I guess we got to do the limiting reactant first. Oh, which is kind of easy on.
Can't you just do it on the ice table?
Huh?
Can't you do the limiting reactant on the ice table?
Yeah, we can do limiting. Yeah. Well, actually, I guess this is the initial. Huh? Yeah, we can do an ice table for this. Oh, well, good enough times I need to mention. Alex, the way Alex explains these ice tables, sometimes they want to figure out whatever is changing and then turn things into fractions, which I'm not a fan of. So like in this case, instead of writing, so I would write this as, this is going to change by negative 2x, this is going to change by negative 2x. Which of those is going to be my limiting reactant? Yeah. So since these are both 2, then I can just look at the concentrations. Whichever one's less is going to run out first. So this will run out first. What Alex would say is basically make this x. So if that's going to be, we'd say like this comes down by x. So this would also come down by x. This would come down by 1/2, or would increase by 1/2 x. And then this would be 4 over 2x. I think it's overcomplicating things.
Yeah.
But I just want you to know, when you see Alex do it that way, you could do it this way too. And now, since we're trying to push things as far to the left as possible, that 0.2 is going to be decreasing by, actually, this is what I would say. Oh, yeah. Because we're making it 0. So 0.200 equals 2x, 0.100 equals x. Although I might even be complicating this more than it needs to be. This is going to be 0.5. This is going to be cool. Everybody tracking so far? So now that becomes our new initial. So we're working from there. And I can change colors. So this is now the initial, so I'm going to have a new change and a new end. So since I basically figured out how do I make all of this as much as possible the reactants, I can now talk about how much is going to shift back towards those products. So this will be minus 4x, this will be minus x. This will be plus 2x, this will be plus 2x. We're subtracting now from those reactants, putting it back into the products. And we did all of this so that we could make sure that the amount of change is small. So we know this is going to be mostly in the reactants. So 0.9 plus even 4 times whatever x is basically going to be 0, so that'll be negligible. Or it's minus 4x. 0.5 minus x is also going to be negligible. And even 0.1 plus 2x is going to be negligible. Because this is going to move, I'm moving such a small amount of this over to that side, because that times 10 to the negative 8, that any of these things that still have concentrations are basically not going to change. And so all of those can be approximated to 0. Otherwise, this might end up being a 4th order polynomial. I don't even know how you solve that. So that means that my equation for K is going to be 0.1 squared times 2x squared divided by 0.9 to the 4th times 0.5. And that equals 4.59 times 10 to the negative 8. And that's a whole heck of a lot easier than what it would have been. It would have been practically impossible. So let's see. Now we can solve for that last x. That's too many zeros.
Sorry.
Okay, so different than before. So before, when we were doing the smallest approximation, trying to figure out if it's less than 5%, we were only approximating one of the x's. Which x out of these three do we need to be worried about being small enough to approximate? Yeah. So the water, right? If I'm approximating the small x, I want to make sure that it's small enough to be negligible. So my smallest number, smallest molarity that I'm changing is what I need to check against. So like, if it's small enough for 0.1, then it's definitely going to be small enough for 0.5, and it's definitely going to be small enough for 0.9. But if I check it for 0.9, maybe it's not small enough for 0.1. So just check for the smallest value that we're approximating. So then this is 6.17 times 10 to the negative 4 divided by and that's times 100. 0.6. %. So it's not even 1%, so it's definitely small enough. And since that's a good approximation, then I can go up here and my final concentrations, what are they? So HCl is actually just going to be 0.900. And then CL2 is going to be 2 times what we calculated for X. Well, also on these, if it didn't come out to be less than 5%, you could plug it back in, and then you would plug it back in for, so like here I left off the x's that we approximated to 0, but it would be 0.9 minus 4, and we would plug that number that we got for x back in, recalculate for this 1x that we didn't approximate, and it would narrow us in. Yeah. Oh, so we had to do the first ice table, and this was, I mean, not the only way to do this ice table. I just calculated how much everything was going to change by in terms of x, and then change everything. But the reason we could do the small x approximation is because we know we've got, well, we've actually shifted the equilibrium as far as it can go in the direction that it's going to be the largest. And that sort of guarantees that our x is going to be as small as possible. Well, now that you're asking about it, like I wonder what happens if, no, we need one of the x's to be, we need one of these to be 0 so that we actually have something to calculate for. If this isn't 0, and I'm instead doing like 0.5, this would still go, actually no, at this point it would go this way. We have to calculate Q. But if all of these have a number plus or minus x, and I approximate all of those to be 0, then I don't have anything to solve for. And then how do I pick which one ends up mattering? Yeah. So it's to find the limiting, and we'll go in the direction towards where the concentrations are going to be highest. So because it's a small k, that's why I went to the left. Because you could do a limiting going to the right, but then it's going to shift a lot back to the left, and we can't do any small x approximations. So like on the next problem is actually, yeah, 10 to the 24. I should just put it down here so I can reach it easier. So this is a really large k, which means that it's mostly going to be products, but I have concentrations for everything in the reaction. So I would do that first ice table and push everything to the products on this one, and then calculate how much it comes back. So it's whenever you've got this really large or really small k. Well, it says 1 to the approximation, and also not have to solve ridiculous polynomials. All right, and the last ones are for you guys to do.
I have one last question for clarification.
Yeah.
So for number 7, when we're looking for which one is the smallest for the 5%, does the coefficients matter, or are we just going straight off the molarity?
Mostly off of the molarity. If there were 2 that were close, then I would go off the one that's gonna, so like if these were like, well, the 2 of them were 0.1, but one of them was like this minus 4x, and the other one was minus 2x, then do the minus 4x.
Okay.
So the rest of the time is yours to either work on these make sure you know what was going on. Or not stay and work on them.
Or you can study for your lab exam.
Or you can study for your lab exam. You can ask questions about the lab exam too.
I have a question on the lab.
Uh-huh.
Question.
Oh, it's like a lab.
Yeah.
This is still recording.